Okay, so these are for heat. If you would, make sure you have your Google Doc that you can copy your notes into. That's really important for us for when we need to have some sort of assessment that you have something that you can reference back to. All right, so let's go ahead and get started. So what is heat? Heat is the transfer of thermal energy from one object to another because there are temperature differences. So we've talked about different types of energy in this unit. We talked about potential, we talked about kinetic, we talked about chemical, we talked about sound, all those types of things. So we start talking about heat, we're talking about that thermal energy. And we know about temperature because we talk about temperature when we reference things that are, outside, the weather for the day. We want to know what the temperature is. That's an actual number value that we're given to this energy. So how does this heat transfer? It's going to go from warmer or hotter things to cooler or colder. So from hot to cold. That's the way heat's going to flow. So when we start talking about temperature, we're talking about a measure of how hot or cold it is compared to a point, okay, some sort of relevant reference point. So when we talk about how hot it is outside, 75 degrees, that's in Fahrenheit. When we measure things in class, we're using degrees Celsius. So when we have the cold water in one of the beginning labs, okay, when it's close to the freezing point for Celsius, it's 0. When it gets ready to boil, it would be at 100 degrees. So those are numbers, and that's talking about how much energy is in that. So temperature is measured by the average kinetic energy, the motion of those particles. We said we're going to use Celsius in this class. There's also Kelvin. One of the first activities we did, we actually talked about how we converted from Celsius to Kelvin with the negative 273. And we talked about how nothing can ever reach absolute zero, okay, 0 degrees Kelvin. The more an object is heated up, the faster the particles inside of it move. So if you remember, we talked about when it was a solid, the particles were very, very slow. And as you heated them up to a gas and it was getting hotter, they were starting to move around. So the hotter they are, the faster they move. Thermal energy is the total potential and kinetic energy, so the stored energy as well as the particles in motion. It's going to depend on what temperature it is, how much mass is there, and whether it's a solid, liquid, or gas. Okay, so that's going to determine what amount of thermal energy we have there. And then we have to talk about as we have temperature increasing, there is expansion. Okay, so because you're getting hotter, the particles are moving further and further apart. Okay, it's going to expand and get bigger. So let's think about something that maybe you've seen before. If you've ever had like a bottle of salad dressing that you've used at supper, so let's say you have a bottle of ranch and you've taken it out of the refrigerator, you've put it on your salad, and you've sat down to eat, and if it's like my family, my kids eat really slow, so 45 minutes to an hour later, we're finally finished with our supper, and we look at that bottle of ranch dressing and it looks like it's kind of bulged out, okay, because as it sat on the table, it has gotten warm, and when it gets warm, the particles expand, okay. At this point in the semester, I typically tell a funny story, and I won't let you go without that. I mean, how could I let you leave me and not tell the story? So one summer when I was in college, I roomed with some folks that I didn't particularly know too well, but we were familiar. We had been to a couple of like Christian campus events together, and so I knew the girls. So one girl, she was absolutely in love with like milk. I felt like the girl could like down a gallon of milk within like a day and a half. I felt like just herself. So she had finished a gallon of milk and she had put it outside the door because she was going to take it down to the recycling the next day. And so it was the summer, and in North Carolina here, it's hot. So she set it outside, I don't know, like 5 or so in the afternoon. At about 10 o'clock that night, all of a sudden, it sounded like someone shot a gun right outside the door. And we, like, just kind of flipped out, like, what's going on? Like I said, I didn't really know these people. I didn't know what was going on, particularly. So we opened up the door, and we couldn't help but laugh because what had happened was the milk carton had expanded because it had gotten so hot. And that little bit of milk that she hadn't quite rinsed out, it just started, to the particles move faster and faster and faster, and it blew that cap off, and it like hit the wall like right outside the apartment. It was so funny after the fact. But anyway, that's my example. It blew it off. So a little bit of rambling here, possibly because it's so late. So as temperature decreases, you have contraction happen. So where they're going to move closer together. So let's think about a driveway. If you have a driveway, or you've ever seen, a concrete driveway or sidewalk or anything, you know that there are these what they call expansion joints, so little slits they've cut out. And the reason for that is as temperature changes, you're going to have the concrete is going to expand as it gets hotter, and it's going to contract as it gets colder. So they cut those joints in the sidewalk, in the driveway, in even roads or bridges. A lot of times students only kind of are familiar with on the bridge when you go over it's like the dunk, the dunk, the dunk. And that's because they have those things that they've cut in so that as temperature changes, that concrete as it expands and contracts, it doesn't cause as much breakage. And so there's my example there, like a bridge has braces to allow for it to expand and contract. Okay, and most of the time you're familiar with that because you know about driving over the bridge and hearing the thump, the thump, the thump. All right, so specific heat. Specific heat is the amount of heat it takes to raise temperature 1 gram of the substance 1 degree Celsius. And so here is a chart, okay? By no means do you have to memorize any of this. I just kind of want to let you know what's going on here. The higher the specific heat, the more heat is required to actually raise the temperature. So let's look at, what do I want to look at? Let's look at this, I was going to look, I thought, here we go, water, okay? So here is my water. Its specific heat is 4.18. That means it's going to take a whole lot of energy to heat 1 gram 1 degree, okay? As compared to something like silver, okay, or even gold, okay? They have a very small number, which means it doesn't take a lot of heat, okay, or a lot of energy to heat it up 1 degree. So if you think about any kind of metal, they get hot really, really fast, okay? But they're also going to cool really, really fast, okay? Whereas water is going to take a long time to, like, think about on the stove, like, heat up and boil, okay? It's also going to stay hot for a while. So the specific heat means how long it takes to heat or cool it, okay? Metals are going to be faster. Things like water, of course, is slower. So then that's what's going on here. And then also aluminum. I like to think about the example. Sometimes I will like heat like toast or something in the oven on a piece of aluminum foil. But when it's in the oven, it's hot really, really fast. Okay, but as soon as I take it out, it's almost instantly cool. Okay, so it'll cool really, really fast too. All right. So here we have the different types of heat transfer. We have conduction, convection, and radiation, and these are ones that you've probably heard of before. So conduction is when you have an object that is touching each other, it's making contact. So if you think about if you have a hot slice of pizza and you put it in your mouth and you eat it, the cheese can burn your tongue because the hot cheese touched your tongue, okay? If you put an egg in a pan and the pan heats up, it's touching the egg, okay? That's how it's going to cook. There's conduction, it's touching it. Think about when you were little and you used to get on the slide at McDonald's when they weren't in the covered little play places. I don't even know if you guys even grew up when that happened, though. Maybe on the playground. Those slides and how when your leg touched it, it was so hot. That was conduction. Okay, you were touching. Convection. This is when particles of the fluid, whether it be a gas or a liquid, move and circulate. So think about like if you have a ceiling fan and you turn it on, okay, or any kind of fan, a box fan, and it circulates the air around, okay. That's going to help. A lot of ovens will have fans. You hear about like those ovens that can cook on your countertop, like the New Wave or whatever, and it's sending the air through, okay, circulating around. Your refrigerator kind of is doing that. It's circulating air around to keep things cool. All right, radiation. This is when energy is transferred by light waves. So when you can feel the heat sort of coming off of it, you don't actually have to touch it. So think about an iron. If you put your hand in front of an iron, you can feel the heat radiating off. It's in waves. You can feel the radiant heat from the sun. Even a microwave. A microwave is going to cook by radiant waves. Okay, it sends those down and it causes the particles to vibrate, and that's actually what heats your food. Okay, but all of radiation is waves. Convection is talking about air circulation. and conduction is talking about touching. All right, so there's a good graphic there. Touching and the conduction, convection, you've got the circulation, and radiation, you got the squiggly little waves. All right, so a conductor, we talked about before, it lets energy go through it well. That heat energy, metals, okay, your tiles. Insulators, they're going to be poor conductors. It's going to kind of inhibit the flow of the heat. Air, wood, and wool. Okay, that's why wool is definitely used as, what people want to wear in winter. And the last slide we have here is on the laws of thermodynamics. The first law says that energy has to be conserved. You can't create it or destroy it. The second law says that energy can flow from colder to hotter if work is done. So remember, typically it goes hot to cold. You can make it go opposite, but you got to add work to that equation. Okay, that's how your freezers and refrigerators work. And the last one, you can never reach absolute zero. Okay, and so that would be there would be absolutely no particle movement, and you have to always have the particles moving, even if they're moving slow. Okay, you can never have absolute zero at 0 degrees Kelvin. Okay, all right, so make sure you turn those notes in, and as always, email if you have questions.